guys, today we're going to talk about symmetry and tessellations. So a lot of the symmetry is going to be something that you've seen before, or it's going to pretty much make sense as something that you haven't seen before. So our first definition to get down is that a figure has symmetry if there is a transformation such that the image coincides with the pre-image. Okay? Now when you guys hear symmetry, what you typically think about is line symmetry. So a figure has line symmetry, or reflection symmetry, we'll call it line symmetry, if it can be reflected across a line so that the image coincides with the pre-image. Okay? So the line of symmetry is also called your axis of symmetry, and it's going to divide the figure into two congruent halves. So for example, if you have a heart, this is going to be your axis of symmetry, and it's going to cut this figure into two congruent halves, or I can take this piece and I can fold it over and it's going to be kind of coincide or be completely symmetrical with the other piece. It's going to lie right on top of it. This is stuff that you guys have seen before. Again, it's really nothing new. It's going to be line symmetry because of the fact that you can have a line of symmetry there. Okay, so the first thing we'll do, guys, is go through and see if it has line of symmetry and draw all lines of symmetry here. All right, so yes, this is going to have line symmetry, and it has one line of symmetry. This has no lines of symmetry. There's nothing I can do in order to fold this thing on top of itself and have it coincide with the other piece. What about this guy? 1, 2, 3, 4, 5. So our starfish here, yes, it has 5 lines of symmetry. The next piece of symmetry we're going to talk about is rotational symmetry. And instead of drawing a line and having it coincide, if it can be rotated about a point by any angle greater than 0 and less than 360, so that the image coincides with the pre-image, then it's said to have rotational symmetry. All right, so basically, guys, what this means is I have my square. If I take this point and I rotate it over this whole square, then it's going to be symmetrical. It's going to lie right on top of itself. I can do it again, I can do it again, and I can do it again. Okay, so the angle's greater than 0, but it's going to be less than 360. All right? Your angle of rotation is the smallest angle through which a figure can be rotated to coincide with itself or to be congruent to itself. The number of times, this is important, this is the one thing that you guys will kind of have to remember when you're doing your homework and when you're doing your review. This is something you may not have heard before. The number of times the figure coincides with itself as it rotates through 360 is called the order. All right, so basically how many times can I move this thing around as it makes a circle and have it lie on top of itself? So if I take it and I twist it once, it's going to be congruent on top of itself. If I twist it twice, if I twist it 3 times and 4 times. So within that 360 degrees, how many times can it lay on top of itself and be congruent? That's what the order is going to be. All right, so we'll go through and just make sure we're good with this concept and then talk about 2 more concepts with symmetry. We want to tell whether it has rotational symmetry, and if so, give the angle of rotational symmetry in the order. Okay, so if I take this guy and I rotate it 180 degrees, then it's going to have rotational symmetry and going to be congruent with itself. How many times can I do that? Once within 360 degrees. And then twice, and we end up back at home. So the order is going to be 2. What about this one right here? Is there anything between 0 and 360 degrees where I can rotate it and it's going to lay on top of itself? No. If it only can do it one time within that 360 degrees and make one full revolution, that's not rotational symmetry. It has to do it within the 360 degrees in order for it to be rotational symmetry. Let's look at this guy right here. If I take this snowflake and I rotate him once, I get rotational symmetry. Twice, 3, 4, 5, 6. Okay? So yes, it has rotational symmetry. How many degrees are in a rotation? 360 degrees. I said that 1, 2, 3, 4, 5, 6 times can it be rotated? So 360 divided by 6 is going to give you 60 degrees. That's the angle of rotation. And then the order is going to be 6. That's how many times it can be rotated and lay on top of itself. The last thing that we'll get down, guys, is plane symmetry. So it's really similar. You're just dealing with 3D figures. If it can take a 3D figure and divide it into 2 congruent reflective halves. All right, so you guys will see this. If I cut that guy in half, these guys are going to coincide with each other. They're symmetrical. Okay, and then the other one is if it has symmetry about an axis. That means that I can take a line, and this figure, this cylinder, can be rotated around this line, around this axis. Again, greater than 0 and less than 360, so that the rotation is going to be congruent. It's going to coincide with the pre-image. The image is going to coincide with the pre-image. So if you guys look at this example here, we want to say if it has plane symmetry, symmetry about an axis. Again, it's like rotational symmetry in 3 dimensions, or neither. Okay, so if we look at this trapezoidal prism, we're basically asking ourselves, is there a way that I could put a plane in that's going to pierce through this to make it 2 congruent halves? The answer is yes. And this is where your plane would go. What about with an equilateral triangular prism? So is there a way that I could slice this with a plane? Take a piece of cheese and pierce through it where it would be congruent? Yes. And does it also have rotational symmetry? Could I put a rod in it and it could rotate around itself and it would be symmetrical? Yes. And let's see what that looks like. So here's your piece of cheese, slicing that, and then here's your rod going straight through it. So if I rotated this piece around the rod, then it would end up being able to rotate upon itself 3 different times, and that cheese is going to slice it to where it's congruent. The top and the bottom are congruent. So that's your symmetry. Now we're going to talk about tessellations. This is 9.6, and we're going to put these 2 sections together just to kind of keep things moving. Oh, let me get this back to where I need it to be. There we go. All right, so I'm not going to worry about the freeze pattern. Okay, so tessellations, y'all. The first thing we'll get down is translation symmetry. Basically, if I take one image, remember a translation is a slide, and I slide it, and it coincides with the previous image, it's called translational symmetry. All right? So if I take one image right here and slide it over, and these guys coincide, if they're congruent, it's going to be translation symmetry. A tessellation is one of these. Okay, so your tessellation, or tiling, we'll use tessellation, is a repeating pattern that completely covers a plane. It has no gaps or overlaps. So if you guys look at this right here, this is your repeating pattern. It's going to cover our plane, and there's no gaps or overlaps between the shapes. Now, this is what is important about tessellations, and this is where we're going to hang out. The measures of the angles at each vertex have to equal 360 degrees. Okay? So the triangle is a good way of looking at it. If this angle measurement is 30 degrees, this is 60 degrees, and this is 90, for instance, and I take these shapes and I move them around to create the pattern, well, this is going to be 90, this is going to be 60, this is 30, there's your 180 degrees right there, and then likewise, there's your 180 degrees. So at each vertex, if I continue this pattern, this adds up to 360. That is important. The same thing happens here, guys. You have 360 degrees here. Each angle measure added up together is going to be 360 degrees. But I think with the triangle, it's really easy to see. So let's see a couple more definitions, and then we'll see how that 360 comes together. So a regular tessellation and a semi-regular tessellation are going to be some terms for y'all to know. A regular tessellation is formed by congruent regular polygons. Remember, a regular polygon has congruent sides incongruent angles, okay? An equilateral triangle, for example. So this is your regular tessellation. These are all the same shapes, and they're going to be all congruent sides and congruent angles. If you guys look at this, this is a semi-regular tessellation. It's formed by two or more different regular polygons. Okay, so these guys are all going to be regular quadrilaterals, and these guys are going to be all regular triangles. So it's going to be semi-regular. Also, it says the same number of each polygon occurs in the same order at every vertex. Let's see what they're talking about here. Blue, yellow, green. All right? Green, green, blue, yellow, yellow. Yellow, yellow, blue, blue, green. So every vertex has 2 squares and 3 triangles in this order. So as you guys start exploring these, you'll see that the patterns repeat themselves. So example 1, the first thing we're going to do is just classify if it's regular, semi-regular, or neither. This one is not a great example, but I'll make sure it's obvious for you guys when we're doing our test. I think that these are a little bit harder to see, but the point is just understanding that semi-regular and regular, the difference between the two. Okay, so classify tessellation as regular, semi-regular, or neither. Well, in this case, I'm using 2 different shapes. They're going to be regular polygons, but this is going to be semi-regular because I'm using 2 regular polygons. Here, I'm using the same shape. I'm using the same diamond shape, and they're all congruent. So in this case, this is going to be regular. And again, this is really hard to see, you guys, but because of the fact that I'm using different shapes, and I know that it's difficult to see on the screen, but these are all not regular, let's see what are those, hexagons. So in this case, it's going to be neither because of the fact that we're using different shapes and they're not all congruent sides and congruent angles. Okay, this is where the 360 is going to come in, y'all. This is the last example that we'll go through. So I want to start with B, actually, and then we'll get to A. One thing I want to remind you guys of is this formula right here. All right, the number of sides minus 2 times 180 is going to give you the amount of degrees in a polygon. This is going to help us, okay? The other way of thinking about it is making your triangles. How many triangles can you make? So if you guys get in a pinch, you can just figure out what your triangles are, okay? But that's going to matter to us because if we look at this right here, remember I told you that whenever you have a tessellation and you have the vertex, it has to equal 360 degrees. So it wants to say determine whether the given regular polygons can be used to form a tessellation. If so, draw the tessellation. Okay? Well, in this case here, this is going to be 90 degrees. We know that because of the fact that there's 4 angles and it's regular. And then how many degrees do I have in this? In this whole, let's see, what is that, an octagon? All right, so let's check it out and see. I have 8 sides, so I have 8 minus 2 times 180 degrees is going to be 6 times 180 degrees, which is going to be 1,080 degrees. Now, this whole thing has 1,080 degrees. 1, 2, 3, 4, 5, 6, 7, 8. I have 8 angles, so I'm going to divide that by 8. That means each angle is going to be 135 degrees. Okay? So this angle right here and all the other angles are 135 degrees. All right, so again, remember this guy right here. Okay, now I wonder if I start putting these guys together, this is what it looks like. For the sake of space, I'll let you guys see the drawing instead of drawing it. But y'all can kind of do some sketches. And what happens right here? What happens at this vertex? What do I have? I have 135 degrees plus 135 degrees plus 90. What does that add up to be? 360 degrees. So yes, based on that, I can make a tessellation. Again, the 360 degrees is what I'm looking for. Let's take the same concept and look at this pentagon. Same thing. I have 1, 2, 3, 4, 5 sides, so 5 minus 2 times 180 degrees turns out to be 3 times 180. If I divide that by 5, I end up getting 108 degrees. Okay, so that means that each of these angles is 108 degrees. So if I put this together, and I repeated this pattern, what would I end up getting? I would end up getting 108 plus 108 plus 108. Well, that's going to add up to 324. Therefore, I can't make a tessellation out of it because there's no way that I can repeat this pattern and get 360 degrees where they intersect. So this to me is the main concept you need to get out of tessellations. You need to think vertex, where they come together, 360 degrees. And that'll help you guys answer this question of yes or no. All right, so this is what we're going to work on in our homework tomorrow, you guys, and we'll review this as well in class.